Hello everyone, welcome to this lecture in the Decision Trees from Scratch series. So, in the previous lecture, we started the process of building a regression tree entirely from scratch. So, let me first revise the problem which we have. So, we are looking at this particular problem where we have collected data from patients. In particular, we have collected this data from patients. We have the drug dose on the x axis, and based on the drug dose, we have to predict the drug effectiveness percentage. That's the problem which we are trying to solve. The data which we have collected is around 20 to 25 patients, which have been shown on these yellow points over here. And it's very hard to solve this problem with a traditional regression model such as ordinary least squares because the data points themselves are pretty non-linear, as you can see from this figure. So it turns out that to capture the relationships between such a non-linear data, regression tree is one of the best algorithms which we can use. So, in the previous lecture, we started building a tree, and at the end, we need to achieve this goal. This is the optimized tree. This is the way it looks like. You first make the classification with dose less than 14.5, then yes, no. Then you make the classification dose greater than or equal to 25, yes, no. And then the final classification is dose greater than or equal to 23.5, yes, no. The real question is how do we get to such a tree? You will see that this tree satisfies all the data points which have been in this plot. But we are trying to answer the question, can we build this tree from scratch? So the goal is that given this training data, we have to build a regression tree that uses the drug dose to predict drug effectiveness. And we started doing this in the previous lecture by looking at the root node. So in the previous lecture, we actually looked at what should be the dose threshold in this first root node. So is it dose less than 11.5, dose less than 26, dose less than 3, dose less than 5? What should we settle on? So we ultimately settled on dose less than 14.5, which should be the root node. And the way we made this decision is we looked at a metric called sum of squared residuals. And we plotted that metric for all the different dosage values. And we saw that among all the different dosage value, a dosage value of 14.5 gave the lowest sum of squared residual, and so which essentially means it gave the lowest error, and that's why we used dose less than 14.5 in the root node. So in the yesterday's or in the last lecture, we have reached this stage where we have determined the root node, which is dose less than 14.5. If you have not seen that lecture and if you don't know what sum of squared residuals is, I highly encourage you to go through the previous lecture. But if you want to follow along, please do because I will explain everything from scratch. So our root node is finalized, which is going to be dose less than 14.5, correct? Up till now, the decision tree looks like this. We don't know anything further. We only know that the root node is going to be dose less than 14.5, and we are going to split the tree into the yes branch and the no branch. We do not know what comes after this until now. In today's lecture, we will build the entire decision tree. In particular, we will look at what comes after this yes and no category. In today's lecture, I'm going to assume that you know the concept of sum of squared residuals, which we calculated in the previous lecture. Basically, what we do is we just take the difference between the actual value of the point and the predicted value and then do the square and then add all of these. That's why it's called as the sum of squared residuals. If you don't know what it means, for now, just intuitively think of it as some kind of an error which we are estimating. Okay, so when you classify or when you first split the tree based on the root node, which is dose less than 14.5, the data point gets split into two halves. There is a half on the left, which I'm calling L right now, and there is a half on the right, which I'm calling R. And now we need to understand what do I need to do further. So let's look at that half on the left initially. So if you focus your attention on the half on the left, you will see that there are 6 points for which the dosage, which is the x-axis. So remember the x-axis is dosage. There are 6 points whose dose is less than 14.5, and those 6 points have been marked in this bounding box over here. So let's look at what to do with these 6 points. So dose less than 14.5 in the yes bucket, if it's yes, the six measurements should come here. And these six measurements are the ones which I've shown here. Let me mark them again with an arrow. One, two, three, 4, 5, and 6. These are the six measurements over here. Now, ideally, what we should be doing is that we need to further divide this into another threshold, right? Like maybe this is we need to make one more threshold of dose less than 3 or dose less than 5 or dose less than 7 in this category. And to understand what that threshold should be, we need to repeat the sum of squared residual steps which we did for the earlier for the root node calculation. Basically, what we'll do is that we'll take these 6 points. So one, two, three, 4, 5, and 6. We'll take these 6 points and we'll start with the set of 2 points. So we'll first start with these two. We'll take their average. So we'll assume first that this is the threshold dosage and we'll find the sum of squared residuals for this. Then we'll take the average of these. Then we'll take the average of these. Then we'll take the average of these. For all these thresholds, we'll find the sum of squared residuals. And when you find the sum of squared residuals for all these points, you can plot the sum of squared residuals for different dosage threshold. So here I have plotted the sum of square residuals for dosage threshold of 3, then 5, then 7, etc. dot 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 up to 11.5. So again, as I said, if you are not familiar with the sum of squared residual concepts, we covered it in a lot of detail in the previous lecture. Just go through that. Or for now, just think of it as an error metric. So this error metric, which is the SSR, is decreasing as you can see with the dosage threshold, right? So for if the threshold is dose less than 3, the SSR will be the highest. If the dosage threshold is dose less than 11.5, then we can see that the dosage threshold will be the lowest, or the SSR will be the lowest rather. The error will be the lowest. So for the dosage threshold of dose less than 11.5, we give the lowest error. So this should be not threshold. Dose less than the 11.5 actually gives the lowest SSR. Great. So it this suggests that when you want to make the further classification in this in the yes bracket or the yes bucket, the next classification should be at a dosage level of dosage less than 11.5. So why did we plot this SSR versus dosage threshold? Because we wanted to understand what value should come here. Is it dose less than 3, dose less than 5, dose less than 7? So that's why we plotted the SSR values and we found that for dose less than 11.5 it's the lowest. So we are choosing this as the question to be asked in the decision tree. So what you will do is that now the dose less than 11.5, right? You will again break it into two categories. You will break it into yes category and you will break it into the no category. So when you further do a split along the 11.5, so 11.5 will be somewhere over here, right? So if you will further split it along 11.5, and there will be again the left side of this, which is dose less than 11.5 and dose greater than 11.5 on the right side of this. Okay. So one thing to remember here is that let me showcase this to you further. Um, if dose less than 11.5 is yes, then the average of all the values which lie on that side is equal to 1. And if the dose less than 11.5 is no, then the average of all the values which lie on the right hand side is 20. Okay, this we don't need these average values, but I've just plotted them here. Now we think that we have got this perfect threshold, right? But there is a problem, and I'm going to explain that problem to you right now. So I want you to look at how many people are there whose dose who are in this bucket over here. So look at this bucket carefully. What this bucket is that dose less than 11.5 it says no, which means dose is greater than 11.5. But for dose less than 14.5 it's in the yes category. So this bucket is the range dose between 11.5 to 14.5, right? And let's look at our graph further. If you look at the data between the dose of 11.5 and 14.5, you'll see that there is actually only one data point here. Actually, let me erase some of the things over here so that it will be much easier for you to actually see. So yeah, let's look at this further. If you look at the dosage level between 11.5 and 14.5, which means between this, let me mark it with a different darker color. Between this green line and this orange line, we are looking in between this, right? There is only one point over here. You see this point. So if again we look at the dosage, if the dosage is between 11.5 and 14.5, which means we are in this bracket, there is only one measurement here, which means that of all the people we have in the training data, there is only one person for whom the dose is between 11.5 and 14.5. And as we have seen in the classification example, that is not good at all. It is a clear sign of overfitting. We cannot have a separate branch just for one person. Remember, the ultimate goal of the decision tree is testing. If any new person is given to us, we need to make sure that our predictions are good for the new person. Now, if there is only one person in the training data for this branch is essentially, no, we are not confident, right, about this whole branch over here. We are not confident because for only one person this branch has been made. So this is a clear sign of overfitting. What if this measurement of this one person is noise and it's not an accurate measurement? It means we are capturing noise and hence we are overfitting. So it turns out that having a threshold as dose less than 11.5, it's not as simple as that. We also need to take care and take into account one more thing. What is the minimum number of measurements for splitting the tree? What this means is that for dose less than, let's say if you calculate the SSR and if you want to split dose less than 11.5, that's fine. But look at the minimum number of measurements for splitting the tree. So for dose less than 14.5, even if, so for dose less than 11.5, if you look in the yes category and in the no category, if you have this minimum number of measurements already set right, then you won't even make that split. So splitting should be done only if there are certain minimum number of measurements. And if the and that value is generally set higher to 20 or something, but in this code we are going to set that value to be equal to 7. So what we are going to do in this particular example is we have less amount of training data. So we are going to say that we are going to split a node further only if the minimum number of measurements are 7. So for example, for dose less than 14.5, it's yes or no, right? What this means is that, so let's say dose less than 14.5, uh, dose less than 14.5, and you have the yes here and the no here. So what this basically means is before splitting this node or before splitting this node any further, I will first see how many measurements are there in the yes category and how many measurements are there in the no category. If there are at least 7 measurements, then only I will do the further splitting. If there are actually less than 7 measurements, then I will stop splitting here and the tree this side ends here. So now with this new criteria, let's actually modify our tree further. So for dose less than 14.5, if you go on the yes side over here, what you will see is that there are only 6 measurements here and we can actually confirm it from the graph. So this is 14.5, right? So if you see on the left hand side, which is dose less than 14.5, there are only 6 measurements, 1, 2, 3, 4, 5 and 6. And that does not satisfy the criteria which we have. There are not, we need at least 7 measurements to further split this node. So for this node, we cannot split it any further. That is why the node on the left will be a leaf, which means that this node right over here, if the dose is less than 14.5 and if the answer to this question is yes, that is going to be the leaf of our tree. We are not going to do any further splitting. It's very, very important for you all to understand this concept because it's not as easy. You cannot just do one more splitting here and think you have fit the tree perfectly. You need to see how many measurements are there. If the measurements are not enough, we cannot split the tree. We should not split the tree because it will lead to overfitting. So we will stop splitting this left branch of the tree and we are not going to split it any further. So what's the answer over here? So if dose less than 14.5, what are we going to say? What is the effectiveness? So that's what we will do next. So if dose less than 14.5, we are on this side, right? We have six measurements and we are not splitting any further. So we have to have an answer. If dose less than 14.5, what's the effectiveness? The simplest thing to do is that you take all these six measurements and you take the average of these six measurements. So I'm just writing this down over here. You take these six measurements and you take the average of these six measurements, and that will be the answer in this of this node or the leaf node. So basically, the decision tree now looks like this. Earlier, at the beginning of this lecture, we only had those less than 14.5 yes and no, right? But when we looked at the yes branch, which is the left branch, we saw that there were only six measurements. So we could not split it any further. The splitting stops here. That's why it's a leaf node. And then the effectiveness will be equal to 4.2%. Why 4.2? Because you take these six measurements and you take their average, and it turns out that the average of these six measurements is equal to 4.2. So up till now we have reached this stage where dose is less than 14.5 in the yes category. The effectiveness is equal to 4.2%. In the no category, let's see what happens in the no category. Okay, so now that we have seen what to do with dose less than 14.5, we have seen that this was a leaf node and the effectiveness is 4.2%. Now let's see what to do about every point on the right hand side over here. Essentially, what to do if the dosage is greater than 14.5. So there are 13 points. There are 13 measurements on the right hand side, which means there are 13 measurements for which dose is greater than 14.5. So since we have more than 7 measurements on the right, we can continue the splitting. Remember, the splitting criteria is that there should be a minimum of 7 measurements. So if you go to this decision tree which we have, for dose less than 4.5, if you go on the left, there were 6 measurements, so it was a leaf node. If you go to the right hand side, there are 13 measurements. So we can continue to split this further. Okay, so now when we split this further, which means if dose is greater than 14.5, let's see what to do. Since we are going to split it into two groups again, we have to find the best threshold, right? Where should the threshold be? Should it be at 15, 16, 17, 29, 30, 40, 50? Where should it be? There are so many points on the right hand side of this. So we will find the sum of the squared residuals for each of these points on the right hand side, and then we will choose that dosing threshold which has the lowest sum of the squares residuals, or SSR. So I'm not showing that calculation for you right now, but what I will highly suggest to all of you is that first take these 2 points, take their average and use that to calculate the SSR. Then take these 2 points, take their average and use that to calculate the SSR. Do this for all the points on the right hand side, and you will see that at 29, so at the dosage level 29, it has the lowest sum of the squared residuals. So when we look at the right hand side, so if dose is greater than 14.5, the next split which we are going to make, we are going to use the threshold value of 29, because the SSR or the sum of the squared residuals is lowest here. Great. So now this is how our decision tree looks like. For dose less than 14.5, it's a leaf node and the answer is 4.2% effective. On the right hand side, we first make the splitting and we decide that the dose of 29, so dose greater than or equal to 29, is the best thresholding to use among everything on the right hand side, and that's why this is the next condition which will be on the right hand side. So this is the next node which we have, that is, or rather the next decision condition, which is we are going to evaluate what's the answer for dose greater than or equal to 29. Now this also splits into yes and the no category. So let's first look at the yes category over here. Let's see what's the result if dose is greater than or equal to 29. So this 29 value I have showed with a blue line over here again. If you see on the right hand side of this, which means that dose is greater than 29, you will see that there are only four measurements, right? There are only four measurements and this is less than 7, and hence this node actually becomes a leaf. So dose greater than or equal to 29, when we go to the yes side, we will not be splitting it further because there are only four measurements here. and so this becomes a leaf. And what is the answer over here? The answer is basically we just have to take the average of these four measurements. So we will take the average of these four measurements and find the effectiveness value, and that turns out to be 2.5. That turns out to be 2.5% effective, and that's the result why if dose is greater than or equal to 29 and we move along this side of the decision tree, the answer is 2.5% effective. Correct? So this is the stage where we have completed almost the entire decision tree, but one branch is still remaining. So, and that is dose is less than 29. So remember, now we are on this category, this side, right, which means dose greater than 14.5, but we are also here, which means dose less than 29. So this side is dose which lies between 14.5 and 29, right? So let's see the number of measurements between 14.5 and 29. So this is 14.5, and so this orange line is 14.5, and this blue line is 29. In between, you will see that there are more than seven measurements between 14 and 29, 14.5 and 29. So this should be 14.5 and 29. There are more than seven measurements between 14.5 and 29. I think there will be eight measurements here, so you can check that. But anyways, there are more than seven, so we can continue splitting further. So we stopped the splitting on this yes branch because there are only four measurements here. But on the right side branch, if dose is less than 29 but greater than 14.5, there are more than seven measurements. So we will further split it, right? And then again, we need to decide what's the decision threshold which we will use uh, between 14.5 to 29. So remember, now we are between 14.5 and 29. There can be many decision thresholds, right? 15, 16, 17, 18, dot, 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 28. So we will calculate the sum of the squared residuals for all these different decision thresholds and plot them. So if you plot this sum of the squared residuals, you will see that for the threshold of 23.5, which means dose less than or greater than 23.5, it gives the lowest sum of the squared residual values. So that's why this will be our next decision point, or the next, rather, the condition which we will be evaluating. So we are here right now. Dose greater than 29. Yes, we already saw that was a leaf no 2.5% effective. But if it's no, which means if dose lies between 14.5 and 29, then we are going to do one more split. And for that, the threshold which we are going to be using is 23.5, because that has the lowest sum of the squared residuals. So the next decision condition is that is dose greater than 23.5, and if it's yes, we do something, and if it's no, we do something. Now let's see what that something is, right? Do we need to split further? So let's see for the yes category first. So now in the yes category, it means that a dose is greater than 23.5, correct? But dose, we are in this section. So which means that dose is less than 29. So this section means that dose lies between 23.5 and 29. So let's see if dose is greater than or equal to 23.5, which means we are in this part, and you can see this has less than seven measurements. So this yes category has less than seven measurements, which I have already written here. Now let's look at the no category, which means dose less than 23.5 but dose greater than 14.5, which means we are in this category. And you can see that here also there are only four measurements. So even in this category here, even in here, when dose is less than 23.5 but greater than 14.5, there are four measurements which are less than 7. So for both of these, we will not be splitting further. These are the leaf nodes. And this is where the splitting of the decision tree stops. This is where we have constructed our final decision tree. And why did it stop? Because for both of these leaves, we have less than seven measurements, right? So we did not, or we should not split it further. That will lead to overfitting, and we do not want that. So now let's see what values to put here. So as always, the to calculate the values, we just take the average of the measurements. So if we go along this side, it means dose is greater than 23.5 but less than 29, which means we lie in this part. So we just take the average of all values over here, and that average turns out to be 52.8. So if dose greater than 23.5, and if we are here, the answer is 52.8. Now let's see if we are on this side, which means if dose lies between 14.5 and 23.5, which means we are in this section over here, what I'm shown with an arrow. And if you take these 4 points and take an average, you will see that all of their values are 100. So the average will also be 100. So if you are in this category over here, which means that dose lies between 14.5 and 23.5, you will see that the answer is 100% effective. And you can see that now the entire decision tree is completed from scratch. And why do we know it's completed? Because now we have all the leaf nodes. There is no splitting which can be done further based on the criteria which we have identified, that for the splitting, the number of members should be at least 7. If they are less than 7, we won't be doing the splitting. Now let's see if this is the same decision tree which we wanted to uh, construct at the start of this lecture. So at the start of this lecture, we looked at this decision tree, right? And we were thinking, how did we construct this? So here there is 14.5, here there is 29, and here there is 23.5. So we were thinking, how did we come up with these numbers? But now you can see our final tree will have the same numbers: 14.5, 14.5, then there is 29, and then there is 23.5. Amazing. So this indicates to us that we have actually completed building our decision tree, and you should be very happy now because we completed this decision tree from scratch. Most of the machine learning engineers which actually implement ML algorithms are not aware how decision trees are constructed from scratch. In fact, they are not aware how regression trees even work. But if you watch this lecture, you now know the process of completing decision tree from scratch. And the way we get these final values, as I already mentioned, is taking all the average in that particular section. So what you learned through this lecture is that not only we built a decision tree, but we learned some key concepts. The first key concept which we learned and which everyone should remember is the concept of overfitting. So if you did not know the concept of overfitting, you would have just have had one more split here. In the if dose is less than 14.5, you would have one more split, and then you will keep splitting the tree. So the tree will keep on growing, and you will of course have a good performance on the training data because you are trying to match everything. But there will be only one measurement in some of the leaves, and that is not good. Which means it will lead to overfitting. Our tree won't perform well on the test data. So today you learned that we need to set some criteria, which means that we need to set some minimum number of measurements which need to be there before we split the tree. If these minimum number of measurements are not satisfied, there is no point in splitting the tree because it leads to overfitting. That is the first concept which you learned. The second concept is the sum of squared residuals. So at several different places I mentioned about the SSR value, right? Sum of squared residuals, which is basically you can think of as an error metric between the decision tree threshold value and the actual value of the point. So two concepts, overfitting and the sum of squared residuals. And if you know these two concepts, then constructing a regression tree will be very easy. This is exactly what's going on when Python actually attempts to construct a regression tree from scratch. From scratch. Awesome. So, hooray. We have now finished building our decision tree from scratch, and this is brilliant. In the next lectures, we will take it a bit higher and we will actually build a tree with multiple features. So, here we have just looked at one feature, right? We have the dose on the x axis, and we have the prediction, which is the drug effectiveness on the y-axis. So what if there are multiple features like the dosage? What if it's also the time spent in the hospital? What do you do if you have two features? How do you construct the decision tree? We'll be looking about that in the next lecture. Thank you so much, everyone. I hope you are learning a lot through these. I'm spending a lot of effort to make these whiteboard tutorials and writing down everything because I've seen that many machine learning tutorials just skip through the basics. They directly go to Python code, and I don't think that's the best way to do machine learning. So please follow along, try making notes, ask doubts in the YouTube comments. I'll see you in the next lecture.